Hello, I'm Nazia Akhtar Bushra and my teammate is Chandrasekhar. Our project is titled AES-128 Hardware Software Co-Design on SoC FPGA. I'm gonna walk you through our project, implementation, design process and results. So let's get started. In this slide, I'm gonna give you a high-level overview of our hardware software co-design system works. On the left, we have HPS, which acts as the controller. It communicates with the FPGA using the AXI Lite interface, specifically the H2F LW AXI master. On the right side, inside the FPGA fabric, we have implemented a set of 64 memory mapped configuration registers. These are 32-bit width and serve as the interface between the HPS and the AES core. The HPS writes the plaintext and encryption key into these registers. Once written, the AES core picks them up, performs encryption in hardware, and writes the resulting ciphertext back into the registers. The HPS then reads the ciphertext through the same AXI interface. This setup ensures tight coupling between software and hardware, allowing high-speed data transfer and hardware acceleration of the encryption process. Config registers. So out of 64 available registers, we used 14 for this project. Specifically, registers 0 to 3 store the 128-bit plain text, registers 4 to 7 hold the encryption key, and registers 30 to 35 capture the 128-bit ciphertext output from the AES core. We also use two special control registers. Register 8 acts as a toggle signal. When the HPS sets this, it tells the AES accelerator to start encryption. Register 36 is the finished flag set by the AES core when encryption is done. The HPS keeps polling the register to know when to read the result. These config registers form the key communication bridge between software and hardware in our SoC design. This is the algorithm overview of our project. The HPS at first writes the key and plain text to the config registers through the AXI interface. HPS then sets the toggle to 1 and waits for the AES core to set the finish bit. The AES core, which was waiting for toggle to be 1, now reads the key and plain text from the config registers, performs encryption, then writes the cipher to the configure registers and sets the finished bit to 1. The HPS, which was waiting for finished, now reads the cipher from the config registers and then clears the toggle bit. This brings the AES core back to the wait for toggle state. The HPS then verifies the result using the software golden reference. If verification is successful, the HPS decrypts the cipher and print the decrypted output. On this slide, I will briefly explain the key design decisions behind our AES implementation. We used high-level synthesis to control the architecture through synthesis knobs such as target frequency and pragmas. To minimize latency, we fully unrolled all loops and mapped all arrays to registers as the latency is the primary objective. Since our use case performs only a single AES encryption at a time, we did not apply pipelining to the AES core itself, as pipelining mainly improves throughput when multiple encryption are processed back to back. As a result, the AES core achieved a latency index of 9 as reported by CyberWorkbench. For communication, we used a fully pipelined AXI4 light slave interface to maximize data transfer efficiency between the HPS and FPGA. During time closure, we observed that setting the cyber workbench synthesis frequency to 50 MHz caused timing violations in Quartus. To resolve this, we increased the synthesis frequency to 66.67 MHz, which allowed the tool to generate an architecture that successfully met timing constraints. Next, this is the post-synthesis result from Quartus Prime. Here we can see our top level entity is GHRD top. The logic utilization in ALMs are 12,522. Total pins are 382. Total registers 7,471. DSP blocks are 0 and total block memory bits is 526336. Result speed up. This slide compares the AES execution time in software versus our FPGA implementation. We measured the average over 100 iterations including I/O with randomized keys and plain text each time. The FPGA AES core takes about 6.5 microseconds per encryption, while the software version takes about 139 microseconds. This results in an overall speed up of 21x, and that is huge. So overall, this project demonstrates how hardware acceleration using HLS and FPGA integration can significantly outperform software implementations for compute-intensive tasks like AES. In next part of the video, I'm gonna boot the board into Linux on the HPS, program the FPGA using Quartus, and then show the AES result by encrypting and decrypting the plaintext hello world. So we are gonna program our FPGA board right now. Let's start. It's 100% programmed, and we're gonna run. Our plaintext is hello world. So this is the result we are getting. So we can see the decrypted plain text is also hello world. So that's all. Thank you for watching.